Hello everybody, welcome to our next video lecture. In this video lecture we're going to be talking about two things. The first is we're going to be implementing a linked list using a linked structure, and the second thing is we're going to design and implement a priority queue using a heap. The first one we're going to code, the second one is going to be like theoretical information, no coding. Alright, let's begin. So I have, on the left side I have a board where I can paint and show you some of the things, and on the right side I have my IDE. Here we're going to be writing our code of linked list. So I have two classes, two Java files. The first Java file is our linked list. It's going to contain our linked list, and the second one is used for testing our linked list class. So first of all, before we begin, I'm gonna write out all the methods that we're gonna be implementing today. So I grouped them into several categories. So first of all, I always like starting with the toString method to just be able to print the to be able to print the object directly and meaningfully. The second one is size, to get the size of the linked list clear and is empty. These three methods are kind of convenience methods that make your coding a little bit more intuitive and maybe easy. The second group of methods, a category of methods, is add first. This method is going to add some element E as a first element to the linked list. And add last is a complementary method to this one, which is going to add the element to the end of the linked list. Remember that linked lists are very good at adding an element to the first position, unlike array lists. And the last method is going to be a method called add, which is going to add some certain element E at the specified index. The third category of methods is our remove. We have remove first, remove last, and remove an element at some certain index. Then we have methods like get first, get last, and get at some certain index. We also have a method called set that's going to take an index of an element and the value, and it's going to change the element's value to E. The next group of methods is contains. We're going to check if some certain element E contains in a linked list or not. Also we have index of, which is going to return the position, and last index of. This method also returns position, but it returns the rightmost position. So you can consider this as you are looking for an element from the left side, and you return the first index that you the first occurrence. This is like looking from the right side, and you again return the first occurrence of the element. And lastly, we're gonna do an iterator method that's gonna allow us to write an enhanced for loop, or for each loop on our linked list. Alright, so we know that linked lists are data structure that contain nodes, right? So we have a node, yeah, let's say 3 nodes. The first, all of them are connected with some links. So we have links here, and we have nodes here, and this is going to be a linked list of nodes, basically a linked list. The first element in this linked list is, we call it the head, and the last one is tail, right? So let me actually write it as fully. Okay, this is going to be like the head, and this is going to be like tail. For short, I'm going to just use the letters H and T when I'm going to draw them. Linked lists come in several different variations. So this one is single linked list because each node only knows what's next after it. when you have a link which goes backwards, like a node also knows which element, which node is like before it. This is called doubly linked list. There are also circular linked lists. You can look at them in the book, in the chapter, in the subchapter linked list, I think at the end. Let me scroll and find it for you. Here are them. So we have circular linked list. So the last, the tail has an tail's next is going to be the head. And we have doubly linked list where we have like links to both directions, like here. And also we have a circular doubly linked list, so you can go forever in one direction or the other direction. Always you're going to be like in a circle. So today we're going to be doing only the singly linked list, where we have a reference to the next element. For a doubly linked list, some of the implementations of methods are going to be a little bit easier. Alright. Also, in order to write our linked list class, we first need to write a class called node. So this circle here represents a node. What is a node? Well, a node is just a holder for the data that the linked list stores. So basically, our node is going to have like the data, right? Like the information that it stores in this list, and we have a reference to the next element. Alright, so basically there are two things inside a node: a reference to the next node and the data. Alright, data also can be a reference if you are storing objects of your own custom class inside a linked list. In that case, it's going to be a reference. But if you store like primitive data types, it's going to be like data. Actually, all of them are going to be like references, because our linked list class is going to be generic, and you know, in generics the parameter type e, for example, is a reference type. That's why it's going to store the references to the information we're going to use. When we have a doubly linked list, there's going to be two references, right? So the first one is going to be to the next, this one is going to be to the previous, and we're going to have the data. Alright, so this is for doubly linked list, this is for singly linked list. Since we're doing singly linked list, we're going to have this kind of thing. So we're going to write this class inside our linked list class, and it's going to be an inner class. And you know, our linked list is a generic type, that's why we add e, and since we're going to be storing elements of type e inside our linked list, node also should be of type e. So the data is going to be as of type e, and also the reference to the next node is going to be, the type of the reference is actually going to be node. That's why it's going to be like this. Alright, and we're going to include a constructor. Let me actually do it with a shortcut like this. And for convenience, let's just include the toString method, the public string toString, where we just return the data.toString. Alright, so this is our node class, and it's complete. What do we do next? Well, we agreed, we discussed that our linked list has two references, head and the tail, like two important variables inside this linked list. So the head is of type node, so that's why we're going to have private node e head. This is going to be the reference to the node, to the head node. This is going to be the reference to the tail node. Also, we're going to have a data field for the size of the linked list, and we're going to store it in that integer. Initially, it's going to be 0. So let's include the constructor. I'm going to again use the shortcut. It's Alt Insert in Windows. Let's include a constructor that that doesn't take any of these data fields. So initially, when we create an empty linked list, our linked list is going to look like head equals tail equals null. Both of them are going to be null. Alright, so if head and tail point to null, it means there's no node inside this linked list. It means it's empty, so we're just going to say size is 0. So yeah, we have our constructor. Now we can construct our linked list. Now let's implement the toString method. Alright, and I forgot to mention that the implementation that we're going to write today is going to be different from the implementation from the book, and probably we may have some errors. It may not be perfect. Some of the things may be very basic. Just as a disclaimer, we're going to build this linked list class from ground up, from zero, from scratch, and yeah, just so you know, not to expect a perfect linked list implementation. Alright? Okay. So toString method. So there are a couple of so we're gonna write if conditions a lot. Alright, so there is a special case when our linked list is empty. We just say if head is null and our tail is null, what's gonna happen? It means that our linked list is empty, and we're just gonna return the symbols like this. Alright, so it means it's empty. Else if, and also we consider when there's one element in our linked list. So when there is one element, it means head and tail both point to the same element. Let me just show you here. Sorry, okay. Let me just show you by an example. So if we have one element, it's going to be head and tail at the same time. So we can just say if head equals tail, it means it's there is one element. Also, we could use size is equal 1, size equals 0. I think they should be equivalent conditions. In this case, we just return this symbol plus head.toString plus this symbol. Alright, so we also can write tail here because they are the same elements. When we go to else, it means it contains more than one element, and in this case we need to write a loop. Well, how do we write a loop? Let me show you by an example. Let's say that we have 3 elements in our linked list. Just assume that there is a link between them. How do we loop? We know that this is our head and we know that this is our tail. How do we loop through all the nodes in this linked list? Well, we're just going to create a pointer. Alright, so pointer, which is going to point to the head, and we're going to do pointer.next. Next time it's going to point to the second element. We're going to do pointer.next to the third element, pointer.next, and we just continue pointer.next infinitely many times. Let's just write it. Node E pointer equals head. Okay, so now we're pointing to the head, and we say while true, do what? Just move it. Okay, pointer equals pointer.next. This moves it but never stops. When do we stop? Well, when do we do next and like the tail's next is going to be null, and this pointer is going to point to null. It means we should stop, right? So we can just say if pointer equals null, just break the loop, right? Or we can invert this condition and put it here. While pointer is not null, just continue doing pointer next. And when like pointer.next is null, this loop is gonna stop. So basically this loop is gonna traverse through all the nodes in this linked list. Alright, now what do we do when we traverse through this linked list? We're just gonna say the string result that eventually we're going to return is going to be containing this left square bracket. Each time we get a new element, we're just going to say res plus equals. We add the element pointer that data, that pointer that the string actually, right? Because it's node plus this symbol, comma, all right? And then we do next, and we added all the elements into this string. And we also added an extra comma in the space for, after the last element. We just need to remove it and add the closing square bracket. We just return res.substring from 0 until res.length minus 2. We just ignore the last comma in the space and add our closing square bracket. Alright, so this should be good. We're going to go back to this toString method and we're going to test it after we implement our add first method, which is right here. Alright, so what is size clearing is empty. The size method returns the size, public int size. It just returns size, right? Public int, it's the next is clear. Public void clear. When we do clear, we just say that the head equals tail equals null, right? Because we just want to remove the reference to both head and tail. Since we remove the reference to them, we're not going to have access to these nodes, and garbage collector is just going to remove all these nodes from the memory. So, and the size, we need to make the size 0 as well. And public boolean is empty. Is our linked list empty or not? We can just say return size equals 0. Now when size equals 0, it's going to be true. It means it's empty. When size is not 0, let's say 2, this is going to be false. It means it's not empty. Alright, so these 4 methods are complete. The next method we're going to be doing is add first. Public void add first. So it's gonna we're gonna be adding an element of type E to our linked list. So how do we add first? Alright, let's go back to our board here. Let's say we want to add as a first element. If there are no nodes, in our linked list, it means the node we're going to add should be the first one, right? So how do we check if there are no nodes? We just say if head is null, right? If head is not pointing to anything and tail is not pointing to anything. Actually, this head is equals null is sufficient. We don't need to write tail null because by our class definition, when our linked list doesn't contain anything, both of them are going to be null, right? So we can just check only for one of the head or tail. Also, we can write size equals 0. But I'm going to stick with this implementation. So in this case, what's going to happen? Both head and tail are going to be pointing to the same node, right? Because like no node, it's going to be added, and head and tail are going to be pointing to this one. So what do? We just say head equals tail equals new node with data. Okay, we have a constructor that takes an element of type E. And since we added one element, we're going to say size plus plus. And else, what happens when there is already one node in our linked list? It's interesting. Alright, so let's say we have one node, let's say we have 2 nodes, and we want to add a new element. And this is head, and this is tail, this is head, and this is tail. So the element we want to add is going to appear here, right? Because it's the first element, add first. It's going to become the new head, right? It's going to become the new head, and its next is going to be the old head. Alright, its next is gonna be the old head. This one's next is gonna be the old head. So we don't have to consider this as a special case. When our linked list has one element, we don't have to consider as a special case. And since it's very similar to the condition when there are multiple elements in a linked list, so what do we do? So first of all, we need to create this new node, right? So we'll just say node E, new node equals new node with that data. So which one do we do first? Do we say head equals new node, and then we say new node dot next equals head? Do we do that? Of course not, because if we do like this, like the new node's next is gonna be itself, right? So first of all, we need to assign the head to the next to this new node, right? So it's gonna be like, let me actually simulate it. Let's say we want to add, this is head, this is tail. We want to add a new node. We create it. After that, what do? We say that its next is head, alright? And after that, we say that head is actually this new node, but not this one, alright? So this is what we do, and also we do size plus plus because we added one element. But we're doing size plus plus in if and in else. In any case, we're doing size plus plus. It means we just can take this size plus plus out of the if body. Alright, so we have add first. Let's test our linked list. So our linked list of integers, I'm gonna use integers for simplicity. Let's say list equals new our linked list. It created an empty linked list. System.println list size should be 0. System.println list is empty, should be true. And also system.println list should just print empty brackets. Alright, 0 true empty brackets. Clear, we're gonna test it after we add some elements. Let's now write a for loop that's gonna run 10 times, and we're gonna say list.add first I. We're gonna add I as a first element. It means it's gonna push all the elements to the right. So the numbers are gonna be in descending order. 9, 8, 7, 6. System.println list. Alright, so we have all the elements. Let's actually print the list and print its size as well, to see if the size is growing alongside with the list. Yeah, we can see that initially it's 0 elements, 1 element, 2 elements. Yeah, everything is working correctly. Now let's do clear. List.clear, and then system.println list, system.println list size, and let's do, before clear, let's do list system.println list dot is empty. It should be false. So false. Alright, we clear, and then it's empty, size is 0. Alright, all methods seem to be working correctly. But remember, we're not doing an extensive testing here. We're not testing for the edge cases. There are probably some possible situations when our methods behave incorrectly. Alright, but for beginner understanding of linked lists, this should be sufficient. Alright, so we completed add first. The next method we're going to do is add last. Data. Well, how do we add an element as last in a linked list? Again, there are two possible conditions, two possible cases. When there are no elements, it's going to be actually we can just copy the condition from add first. When there are no elements, it's just going to be a new node, right? And also we can just do size plus at the end. When there is an element, let's say there is one element and let's say there is two elements. This is head and this is tail. This is head and this is tail. The new element we add is going to be green. Alright, so when we add new element, what do we do first? Do we assign this link first or do we do it as a tail? If we assign it as a tail, we're going to lose reference to the previous element. That's why first we need to establish a link. So we say this new node, the tails next is going to be this new node. Tails next is going to be this new node. And this new node is going to be tail. Alright, this new node is going to be tail. That's it. So first, we create this node data. And then what do? We say that the tail.next equals new node, and then we say that the tail is going to be new node. Alright, so these three lines of code are going to ensure that we add elements as last. Let's actually do add last here. It should change the order. It should be from 0 until 9 in increasing order, if it's working correctly. Yes, it's working correctly. The elements are being added in increasing order. Alright, now let's move on. The next method we're going to be doing is add last index e. Public void add, it's just add in index and e data. Alright, so what do we do in this case? This is a little bit more tricky to do. We need to check the index for validity. So how do we check index? So before checking this index, let's first analyze what add does. So when we have our nodes, what does it mean to add to some certain index? We can add an element here. It means it's going to be the new first element. We can add element here in between these two nodes, here and here. Right? This one is very similar to add first. Actually, it's exactly the same as add first. This is exactly the same as add last. So we can consider them as special cases. Also, know that this index is 0, this is 1, this is 2, and this is 3. And you can already see that our index here has to be greater than or equal to 0 and less than or equal to the size of this linked list. Otherwise, this is an invalid index. Alright, so we can just say if index is less than 0 or this index is bigger than size. In this case, we can throw a new array, or do we have list index out of bounds exception? No, array index out of bounds exception. Alright. So now we are 100% guaranteed that index is correct. So if index is 0, it means it's the same as at first. We just call at first data. Else if index is the last, if it's equal to the size of the linked list, it means it's the same as at last. In all other conditions, it means we are adding somewhere in the middle. Right? So how do we add an element into the middle of a linked list? Alright, so since we have only the forward link, let's say we are adding an element here. Since we have only the forward link, we need to kind of put a link here and then a link here, right? So we need to find a place, it means this position here, where we can do this is next is going to be this one, it's next is going to be this one. So basically we need to find a node which is located at index minus 1. Okay, so this is 0, this is 1, this is insertion point 2, and index of the node where we need to move until should be index minus 1, right? This insertion index minus 1. So we need to write kind of a loop which is similar to the loop we wrote in toString. So again, first of all, we create our node, a new node equals new node data. After that, we do some repetition. So we're gonna be initially located at this index, right? So it's gonna be like a node e pointer equals head. We need to move it how many times? 1 times, 2 times, 3 times. For an insertion index 2, we need to move it only once, right? So index minus 1 times, we need to shift it to the right. So we do while. We need a counter, right, by the way. Int I equals 0, and while this I is less than index minus 1, because we need to repeat it in index minus 1 times, what do we do? I plus plus, right? So we are guaranteed that this loop repeats I index minus 1 times. What do we do index minus 1 times? We move this pointer so many times. So we just do pointer equals pointer dot next. Alright, so after this loop, we're guaranteed that we are located at the node after which the element would be inserted. So what does insertion mean? It means that the new node's next is gonna be this node's next is gonna be this node's next. It's pointer dot next. And this pointer's next is gonna be this new node. And after we do this insertion, we just do size plus plus because we have added an element. Alright, so let's test our hypothesis here. I mean test our code here. Where I'm gonna remove these guys here. Let's just say list.add first 2, 3 times, and then we're gonna add to in index 1 an element I. So we should have something like 1 and 0, 1, 2, 2. Yes, it's correct. So we add 0 at one index, 1 at one index, 2 at one index. Alright, so each time we add it to the one index, 2. So it's now they're being added to the second index. To add it all the way as a last element, we just do index as list.size. Alright, so it's gonna be like add last. Alright, so we can see that they're being added as a last element. Okay, so add is ready. The next method that we're gonna work on is remove first, remove last, and remove at index. Public void remove first. Let me just copy it. Remove last. And remove at some certain index I. Alright, so what does remove first mean? Removes are actually kind of easier to implement, but there are some special cases. When there's no element in a list to remove, we can't do anything, right? So we just say if size is 0, yeah, this time we're using size, throw new no such element exception, okay? In this case it means nothing to remove. And if size is 1, let's consider as a special case. If size is 1, it means the head and tail are going to be both null. The size is going to be 0. Okay. Else If size is not 1, it means if it's bigger, then what do we do? Let's look at it graphically. So let's say these are our nodes. What does it mean to remove the first element? So this is head. It means just assign this as a head, and this is going to be lost. Okay, so how do? We just say head equals head.next. Alright, so head's next element is going to be the new head, and we can safely do size minus minus. So this is remove first. Now let's complete all 3 remove methods and then test them. Remove last. So here it's kind of like the first 2 conditions are same, because yeah, they're very identical. And when size is bigger than when the size is bigger than 1, this is a little bit tricky and not similar to remove first. Let's say there are some elements here. Yeah, this is going to be our tail. So we can't just assign this as a new tail because we can't get the previous element of tail. Right? We can't get the previous element of tail because it's a single linked list. So it means that we need to go up until the last element. I mean the element which is before the last element, and assign it as a new tail. So we need to move our pointer until this pre-last element. So we know how to move our pointer. We're just gonna create our pointer to head, and we're just gonna say while pointer.next is not tail. Yeah, while the pointer's next element is not tail. If it is tail, it's gonna stop. We're just gonna say pointer equals pointer.next. We're just gonna move it, and we're guaranteed that pointer now is located at the element before tail. After that, we can just say the tail is gonna be, the new tail is gonna be this pointer, and tail's next is gonna be null. It's important because tail doesn't have the next element, and which is the size minus minus in this case. Alright, okay, should be good. Now let's do remove at some certain index I. This probably is one of the hardest methods to implement in a linked list, but we're gonna do it. There are a couple of special cases. First of all, we need to check this index. So, and it's not unlike add to some certain index I, right? Because now indices should be between 0 and size minus 2, size minus 1, right? Because it's not in between the elements, it's directly the nodes themselves. So we can say if the index is bigger than or equal to 0, and the index is less than size, alright, it's a condition when the index is correct. When we invert it, we're gonna get the condition when the index is not correct. In this case, we can just say throw a new array index out of once exception. Okay, so in this case, the index is not valid. Also, when the size of this linked list is 0, it means there are no element to remove. We can just say throw new no such element exception. Alright, and when the index is 0, it's the same as remove first. When index is size minus 1, it's the same as remove last. So these are kind of special cases. When size is 0, what do? We just do remove first. Else if size is equal to index minus 1, sorry, not size, here should be index. Index is 0 and index is size minus 1, we just do remove not first but last. And in all other conditions, it means we are removing an element from somewhere in the middle of the linked list. So how do we do that? How do we remove this 1? let's say we want to remove this element here. Okay, this element right here. It means we just need to make this link. Okay, we need to establish this link. It means we need to go and up until this node, until this index. All right, so again we're gonna start from the head. We're gonna have a pointer. Okay. Also, we need to have some variable for counting how many times we're doing this moving operation. Int I equals 0, and we're gonna say while true for now. What do we do? Pointer equals pointer dot next, and I plus plus. Okay. So I is gonna store how many times we repeat this operation, and pointer that next repeats this movement. Okay, so let's actually draw another case. Alright, so let's say we want to remove this element here. It means we need to move up until this place, right? So we started here. This is 0, this is 1, this is 2, this is 3, this is 4. Remove 3 means move 0, 1, 2 times, right? So remove 4 means move 3 times. Right? So here we can just write remove index while I is less than index minus 1. Alright, so while index minus 1, move it. So this guarantees that our pointer is now located at this position before the element which we need to remove, and this pointer's this element's next is gonna be this one. Alright, so what do? We just say pointer.next equals pointer, you're gonna like this one, pointer next. It's like C++. Also, we don't forget to do size minus minus. We don't do size minus minus here and here because they're already implemented inside the method. Remove first and remove last. So this should be good. Let's see how it works. So we have our list. Let's just print it for to just see. Okay, there are 13 elements. We're gonna say while not list that is empty. We have this is empty method. While it's not empty, we're just gonna remove the elements from the beginning. List dot remove first, and system.println list. Okay. All right, so we are able to remove the elements from the beginning. Let's do remove last. All right, so we can remove the elements last, and let's just say while list.size is bigger than, let's say, 3. Okay, up until the last 3 elements, we're gonna remove at index 1. Okay, always we're gonna remove an element at index 1. So here 2 is removed, this 2 is removed, this 0 is removed, this 1 is removed, 2 is removed. It seems like it's working correctly because the 0th element is being preserved. Alright, very good. Now we're on we're almost done. Get first, get last, get set. So we need to do get first now. You can click this Ctrl Shift and minus, and it's gonna minimize these methods. Public E get first. So it just basically returns the data which is stored as the first element. We can just return head.data. It's very simple. Public E get last. This is also very simple. It's just tail.data. Okay. And get at some certain index. Public E get at some certain index. Well, we know this. So in order to get an element at some certain index, we just need to move this pointer to that index, right? It's actually very simple to this code we wrote here. I'm just gonna copy it, okay? Copy and paste it here. So we have a pointer to head. I is at 0, but we repeat not index minus 1 times, but index times, because we need to move up until that position. So if it's like 3, we do 1, 2, 3. Okay. And also, I forgot to do that, we need to check if the index is correct. So we can actually take this two conditions. We can also take this one, because if there is no element to get, we should like throw no such element exception. It will make sense. It will make sense. Alright, so here what do we do next is we're just gonna return pointer.data, because our pointer has moved up until that position. Let's test this get first and I'm sure get first and get last work correctly. Let's just see get method. We're just gonna write a loop that's gonna run up until the list size, all elements in system.println list get I. Okay, we're gonna get each element one by one and print them. So we started with 2, and let's actually print them on a single line so we can compare our initial list and our printed values. Alright, looks correct. There are 13 values. Get is working correctly. Now let's do the set method. Public void set int index, and there's some data e of type E. So it's very similar to this one, because we need to move up until that place, right? And also we do the same index checking. But we don't do if size is 0, because we're actually we need to do no such element exception, because we're setting, not adding. It's different from adding, because actually we're changing the element. Adding is going to insert, but set is not going to insert. It's going to change the value of the existing node. So we moved, and what do? We just say pointer.data equals data. So let's test this set method. We're just gonna do list.set index I to value I. Okay, so each element is just gonna take their index value. It should be like 0, 1, 2, 3, 4 up until 12. Alright, it's correct. Okay, so these four methods are done. These four methods are done. Contains index of, last index of. Public boolean contains. I'll just return false for now. Public int index of, return -1. Public int last index of, return -1. Okay, so contains actually takes the data, right? It returns true if our list contains this data, otherwise it returns false. So how do we do that? Well, we just need to traverse through our linked list. We're gonna have a pointer to the head, right? And while this pointer is not equal to null, we're just gonna do pointer equals pointer.next. Alright, so basically it's gonna travel through each node one by one. What do we do while we're moving? We say if pointer's data equals to the data, we just return true, right? And if when this loop finishes and we don't go inside this if loop at least once, right, it means there's no such element, and we can safely return false. Contains. We can just call this method tested list system.println list that contains I. So basically it doesn't contain 10, 12, and 10, 11, and 12, right? Yes, all other elements are present here. All of them are true. Okay, now let's do index of. It also takes the data, and now we need to return the index of the element. So what do we do here? So Let's say we have an index which is equal to 0. Yeah, let's say it's not index but I. And we're gonna have a pointer. This is gonna be the result that we're gonna return, okay? And we're gonna have a pointer to the head, and we're gonna move our pointer all the way until the end. While pointer doesn't equal to null, we're gonna do pointer equals pointer.next. And while we're doing it, we're also gonna increment I, right? We're also gonna increment I, and we're gonna say if pointer data that equals the data we're given, we can safely return I because we found it. But what if we didn't find it? If we didn't find it, we usually return -1, right? We usually return -1. So is it gonna work? Let's just test it. List index of. So since we're getting all the elements one after another, it should be the second element. Wait a second. So we're checking I, right? 0 is located at 3, 1 is located at 4, 2 is located at 0. Yeah, it's like index of, it returns the first occurrence. 10 is not here, returns -1, 11, 12. It looks like it's working correctly. It looks like it's working correctly. Alright. Looks like it's working correctly. Last index of. So here we also have some data. So last index of, we're gonna have almost the same implementation. Let me actually copy it. It's gonna be almost the same but different. Okay. So we're gonna have another element called index that's gonna store the index of the variable. Instead of returning it, we're just gonna say index equals I. We're gonna record it, okay? So since we have a return, it's gonna break in the first occurrence of the element when it's found. So it's like the first occurrence from the left. When we don't break, it's gonna be the last element, right? It's gonna be the last element, and we can just safely return here the index that we just found. Alright, it should be good. Last index of. Now last index of for 2 should be 0, 1, 2, 3, 4, 5. It should be 5 instead of 0. The third element should be 0. Sorry, 5. It should be 5. 5, yeah. Alright, that's very good. Okay, what are some other methods that we need to do? The last one is iterator. So iterator is actually a method from the iterable interface. So that's why we're going to do implements iterable. Iterable E, sorry. We don't have this iterator, let's just remove it. It asks us, it says an error, yeah? It asks us to implement this abstract method called iterator. Public iterator E iterator. So from here we need to return an iterator, okay? From now we can just return null and we don't have any mistakes. So this is an interface. It means we need to implement, we need to write a class that implements this interface. Public, let's call our class our linked list iterator. Sorry, not public, class, yeah. Class our linked list iterator implements iterator, and we need to implement its abstract methods. I'll insert implement methods, two abstract methods, has next and next. Has next gives us true when there is a value to be returned, okay? Next returns the element that that we can next just returns the next element. Okay, so here we need to have a node, private node. So each time we call this method, it's going to return us new iterator. It means it's basically gonna be an iterator that's always starts from beginning. Okay, so it's gonna be head. Sorry, it's gonna be pointer equals head. Okay, the head of the of this linked list. Why we can write head? Because this is an inner class. It has the access to this data field called head. Pointer head. Has next means what? If this pointer is not null, it means we have an element to read, right? Okay. If it's like 0 elements, it means it's null, false, right? If it's at least 1 element, it means it's true. Okay. So, well, how do we return the next element? First of all, next means also it moves this iterator by 1 position to the right. It means we're going to do pointer equals pointer.next. But before moving, we need to return the value which is at this pointer, right? So we can't just return should be the last statement. Usually it's the last statement. That's why we first save it in a variable, and then we move it, and then we return this data. So this should complete our linked list iterator, and when the method called iterator is invoked, we just return new our linked list iterator, and this should complete our iterator method. Let's test it. So now instead of using this indexed notation, we can just use enhanced for loop. For each integer I in our list, we can just system out println I. And you can see that our list is being printed. Alright, so this completes our implementation of linked list class. We wrote approximately 280 lines of code. All of the code is here. And these are the methods that we have completed. Yeah, I think that's it. Now let's talk about the next thing that we wanted to talk about is priority queue. Well, priority queue in Java is implemented using a data structure called heap. You can see it here. Heap. Heap is a special data structure. It's also used in heap sort. Basically, what is a heap? A heap is a data structure that it's actually like a binary tree that arranges its data in some special order. I think this could be a nicer example. So you can see that each node actually has 2 childs, left child and right child, left, right, left. Some of them might not have any childs at all, some of them might have only 1 child, and this one is called root for these 2 children. For both of its children, it's called like root or parent. So for a heap, there is a condition called heap condition, where the parent is always bigger than its children. Right? So 50 is bigger than 30 and 15, 15 is bigger than 10 and 5, 30 is bigger than 19 and 20, 19 is bigger than 2. So heap condition is true for this particular arrangement of values. And if we write it in a list, it's going to be like 50 and then 30, 15, and then 19, 20, 10 and 50, 10 and 5, and then 2. So basically you just take all the elements one by one from left to right on each level. From level 0, from level 1, from level 2, from level 3, and write them down in a linear fashion, and you get this list. Okay? And this list in this special arrangement is called heap. Okay? So this priority queue uses this heap. Why does it use heap? Well, because the first element in the heap is always the maximum. It's always the maximum. That's why, since we're using priority queue, the highest priority element is always going to be the first one. That's why when we do dec queue, it's just going to be linear time. NQ is going to be logarithmic time, and get size is going to be linear time. It's going to make this priority queue very fast. For any given list with some random allocation of elements, in order to convert it into this into an arrangement where the elements are allocated correctly, the heap condition is true. To make the heap condition true for any given arrangement of values in a list, it takes a logarithmic time. So let's say that the values are randomly located. In order to make them satisfy this heap condition, the algorithm takes logarithmic time. That's why it's very efficient to use heaps in priority queues. Alright, so thank you guys for your attention. Today we talked about two things. We implemented a linked list using a linked structure completely from scratch. We implemented all the methods. As I said before, this linked list implementation is not perfect. I am 100% sure that it's not perfect. There are many things that could be improved in our implementation, and it's also different from the implementation from the book. The second thing we talked about is a priority queue using heap. Its implementation is very simplistic because kind of like we are using a ready-made data structure called heap. If we had to implement a heap data structure, it would be a little bit more difficult, and it's a story for another video lecture. Okay, thank you guys for your attention. Thank you for watching this video until the end. Thank you for your patience. Have a great day and good luck. See you guys.